Hi everyone. So today I'm going to be talking about the topic of reinforcement learning and control and reinforcement learning through inference and graphical models. And this lecture, there's actually two parts to it. So it's split up into two different lectures in the course. And both of them are given by guest lecturer Moran, who is actually a PhD student in Professor Eric's group. And this topic is actually the fifth module in the series. And the goal of the lectures are to give a gentle introduction to the basic concepts of reinforcement learning. And it's focusing on the connections between control and inference in probabilistic graphical models. These are some additional resources. So if you are interested in learning more about any of the materials covered, this is actually covering a large range of concepts in reinforcement learning. So there's not that much of time spent on each and every aspect, but if you want to learn more details, you can visit any of these resources. And before we get started, I just wanted to say that the topic of reinforcement learning actually has many applications, and it has been used in several domains in the past. So this is just to show you an example of what that is. It's not the focus of this lecture, but just to tell you that this is an important topic, and it actually has come up previously in text generation, in the framework for the entropy regularized policy optimization framework, where we observed a loss function looking like this, where this is the generative model for the text, and this is the expectation of a reward term, where we have y's for the better generated text, and then our gold standard is this y star here. And that's actually of this kind of form, where this f of x is and when we take the expectation of that, that's actually a stochastic objective. So this is one example of RL showing up. And the plan is, there are two parts to this, but actually these lectures will only mainly focus on the first part, which is to give this introduction of reinforcement learning and control as an inference framework, and then connecting it to the concept of variational inference. So this is pretty general for machine learning, but we actually have different kinds of learnings. First one is supervised learning, where we have a set of data where the observations are the x, and then we have the labels being y, and the goal is to learn a model that approximates the probability of y given x. And in unsupervised learning, we just have all of the x's, and then we want to kind of learn a model that approximates this joint distribution. And that can be used for various things, such as computing conditional sampling from distributions, things like that, which could be important for various downstream tasks. And both of these kinds of learnings are actually decision-making assistive tools. And then we have reinforcement learning, which we will talk about today. And this is just a diagram kind of giving a high-level illustration of this, where we have an agent that interacts with the environment, where it takes a state S from the set of S and actions, and then it interacts with the environment to get back a reward, and it transitions to the new state S prime. And the goal here is to learn a policy which will transition from one state to another by taking certain actions, such that we maximize the utility, or in this case, the reward function in the given environment. And ultimately, the goal is the following, that we have an agent that can intelligently perceive and interact with the world and has useful goal-directed behavior. And it will, of course, be able to learn from its current actions that it takes, and say revising the policy, which we will actually talk about later through like policy iteration, looking at policy iteration, value iteration, and then Q learning. And then, of course, adapt to changes, and then be able to plan and maximize the utility functions. And RL is a useful framework for being able to do these various things. And the task of the, the, the domain of RL actually has shown a lot of success. For example, in learning to play games, we have agents who can even successfully beat one of the best human players. And it has also shown a lot of success in, say, the domain of robotics, where we train the agent in simulation and then kind of transfer that learning to the real world. And it's also been successful in imitation learning or behavioral cloning, where we kind of teach it some task from the expert behavior, and it has to be able to imitate that or reproduce that. Okay, so just after the motivation, now we're going to talk about some of the basic concepts in RL. So actually, this environment, it follows a Markov decision process, where we have a set of states S, and the agent is given a set of different possible actions A. So it takes it senses the states and the rewards from the environment. It then takes an action, and then after that, the agent is able to obtain a reward, and then it transitions to the next state as t+1. And in the environment dynamics, that's actually following Markovian dynamics, where the probability from going from one state to the next state is just dependent on that immediate previous state, and then the current action, but not the states before that. And it also has a reward function, which we denote this way. This is the expected reward in the next time step, given that the agent takes a current action from the state. And when we talk about trajectories of the agent, we are basically referring to these various kinds of variables, where we have like a tuple of states and actions, and then the corresponding rewards in this form. So the question is now, what can we use these Markov decision processes for? So first thing is we can use it for policy search, which is to find some sort of useful policy from one state, taking an action from a state. And so in this case, it outputs actions for each state such that we have a cumulative reward, and we want to try to maximize that. Now, the other use of RL is actually inverse RL. These lectures do not talk too much about it, but the idea is that given a set of optimal trajectories, we want to be able to infer the corresponding MDP. So in this case, we want to ask questions like, what is the reward function that the expert optimized, or what is a transition operator? So in other words, it's the probability of the state st+1 given the current state st and the action at. And in policy search, there's actually two different kinds. There's first deterministic policy search, where the action is dependent on the policy of the given state. And then we have stochastic policy search, where the actions are following this underlying probability distribution of the actions given the state under that policy. So we will actually talk about both of these kinds in the coming slides. And the goal of RL is we actually want to be able to maximize the return or get the maximum possible cumulative reward. And we can write that in the following ways. So say we start at this time step t, we can just denote gt to be the summation of all of the rewards from the current time step till the end of the horizon, which is capital T. And we want to make sure that this sequence actually converges to something finite. So in order to do that, we introduce this gamma variable, which is which we call that as the notion of discounted return. So for all of the subsequent terms, we kind of use gamma in this way. And we can rewrite this summation as follows. And recursively, we can express the same sequence as this RT plus 1 plus the discounted reward in the next time step. And here we have gamma to be from between 0 and 1. And we call this a discount rate. Okay, so we will actually be using this following this when we compute the value functions as well as the Q functions. So we can define the value function of a state S as V pi S. So this is under a policy pi given a state S, and this we can interpret this as the expected return of the state S by following that policy. And it's can be rewritten like this as the expectation of the policy of GT, which we had just computed here, given the state ST. And we can rewrite it this way, again, following this. And when we talk about a value function, we also refer to something called this Q function, which is very similar to the value function, except it's the expected cumulative reward from a state once we also take this action A. So it again looks very similar, but we also have this additional term here of this action. And we can express it in this way. Now, if we want to get the Bellman equation for this value function, we had this from previously, we just looked at that. And this is actually called the stochastic objective. And it's very similar to that RL framework that I was talking about in the very beginning, which is basically of this form here. Okay, so we can write it in this way. Again, this is just following this recursive relationship here. And we can rewrite this as a summation of the action taken by the policy. And this is basically the transition operator. So it's a transition that's weighted by the probability of taking that transition and then also taking this action of this policy. And then we have this reward plus the gamma discounted return in the next time step, which is T plus 1. And this is basically gamma of the value function in the next state. So this is just this we can rewrite to be this. Okay, so what this is just more of a computation tree, just describing this. And what it is that we start with the state S, which is, say, this node kind of denotes that, and then we kind of enumerate over all of the possible actions that we can take, And so these black nodes are state and then action pairs. So imagine that we kind of store this in like a table, all this information. And then once we have that, the actions and the state, then we can go to the next state. And in this way, we can kind of unravel this entire tree. And then once we want to compute the value functions for each of those states, you can think of it like we are kind of going back to the root nodes. So we are expanding out the whole tree, and then we are kind of rolling back up. This is just an example of what an MDP looks like with the value functions and the Q functions. So for example, let's just consider this case where this is a 5x5 grid world of states. So each of these cells here are each of the different states. And this is just the value functions for each of the states. So we can see that if we start in A or the B grids, we are actually getting the maximum amount of reward. So the agent in this way would be able to learn to, if it needs to maximize its reward, it would need to like start in one of these. And then once we go lower, we will kind of run out of the grid. So this is kind of like this negative reward. Okay, so let's talk about the Q function now, given that we just looked at the V function. So we have, again, it's the cumulative reward of the state given that we take some action A. And we represented it like this from the previous slide. And again, we can rewrite it like this with the reward plus the discounted expected reward at the next time step. This is the GT plus 1. And we can write this in a similar way, just like we looked at the value function for the policy. Except the only thing we have in addition is we also have the action terms. And then we can essentially write it this way. So this is like kind of like a recursive formula where we have this Q term here, but we also see coming up here. But this is the Q function for the next time step and the action. And this also looks similar to like in the value function. So again, these are, instead of just having as, we have the state and the action, the pairs. That's why this is a black node. And then we obtain some reward from taking an action from that state, and then we go to the next state. And again, we can kind of expand upon this whole tree and then go backwards to the root nodes until we compute the Qs for each of these higher order nodes. Okay, and there's another thing that I also wanted to define, which is the idea of optimal functions. So in this case, it's the optimal value function, the optimal Q function, and then once we talk about this, then we will be using all of these different functions. Okay, so in general, solving an RL task, it means that we want to find an optimal policy that achieves high reward in the long run. And when we say that a policy is better than or equal to some other policy, just call that pi prime, that means that the expected return, or in other words, that value function from that state is greater than or equal to that of pi prime for all of the states. S in the set of states S, capital S. And now we can look at optimal value functions. So when we say that we have an optimal value function from a state S, that is basically meaning it's the maximum of the policy that gives that largest value or expected return. And we can write this in this way as the max over all of the actions of, this is the transition operator, and this is the reward and the discounted expected return of the next time step. And if we just compare the two functions of the regular value function given a policy pi, so v pi s, and then compare that to the optimal, there's only a few differences. The first one is, instead of kind of summing over all of these actions, we do the max of that, because we want to kind of get the optimal reward. And then here it's again, instead of v pi s prime, it's this v star s prime. And then very similarly, same thing for finding the optimal q. And if we were to think about these two functions as we thought about using the computation trees for v pi and q pi s sa, we can look at it like this. And the only real difference between this and the previous computation trees are that we're essentially doing this max operator here of the max of the actions. So it's like we take all of the action and then we get the maximum of that. And then similarly for Q as well. Okay, so it's also possible for us to recover an optimal policy. Let's call that P star of A given S from the optimal Q function. And actually, the lectures do not go too much in detail about this, specifically what this Dirac delta function is. But it's basically that there is a relationship from, if we know what this optimal Q is, we can kind of take the R max over A of that Q function to get that action, and then kind of compute the Dirac delta of that action, and we were able to get the optimal policy. And to recover a set of optimal trajectories, we can just execute the optimal policy if we have that. So just to remind you again, the optimal trajectory are the set of variables, which is a state, the action, and the reward for all of the different states. And here's just an example of a grid, the same grid world, but if we have, say, an optimal policy. So again, each of these cells are states in this 5x5 grid world, and this is, for example, what the optimal value function looks like, and then we can get the corresponding optimal policy. These are the different actions we take from each of the states to get to the next state. Okay, so just a recap of this information. First, we have agents that interact with the environment, and the environment follows the dynamics of a Markov decision process, where the transition of the agent from one state to another just depends on the previous state and the action. We denote this to be the initial state, and this to be the transition, and the policy which follows this probabilistic distribution of an action that's under this policy, and then we have a reward function. Okay, so now let's talk more about MDPs. Specifically, we have different states and actions, and the states the state transitions follow this Markov transitions. But if we want to just compare between like Markov decision processes and Markov chains, it's actually very similar. It's that if we just take the states, this actually is forming a Markov chain. And the states and the actions, as we will see later, are actually random variables, and they can be, say that they're sampled from this policy of A given S for the actions. And then we have the states that are sampled from the transition dynamics of the environment. Now the question is, how can we define a distribution over a rational and or optimal trajectories? In other words, given that when we go from one state to another by taking an action, the agent gets a reward, is there some way that we can ensure that trajectories that have higher rewards, we will give more weight to those, and then trajectories with lower rewards, we will give less weight to it. So we're going to actually explore this idea. Okay. So what we will do is we just looked at this MDP, and what we're in addition also going to introduce is this idea of this hidden Markov model, where we will also introduce some additional variables, which are referred to as optimality variables in the lectures, and these are actually observed, and they have a direct relationship to the reward. And the actions, the remaining variables, which are the actions and the states, are hidden variables. And so this is the same as we saw before, but the additional thing we introduce is the idea of optimality, which is we have this notation here, which is P of OT. So the optimality variable at time step t, given the state in action, is the exponent, the exponential of this reward function. And the interpretation of this is that if we get a high reward after taking an action from the state, then we are more likely to be optimal at that particular time step. And this is actually called what is known as soft optimality. Okay, so now it's why is this model useful? So actually these optimality variables are important because by how it's defined here, they actually inject information about the reward into the probabilistic generative process. And they can actually help in various things, such as being able to find the optimal policy, or for planning problems, such as what is the next action to take given that I'm in some particular state. So in other words, I would be finding various trajectories and determining which one as the agent is the best or optimal trajectory, and then kind of picking an action that's part of that trajectory. So it can be useful in like a planning problem. And it also has various other applications. And we will actually look at this more in detail. So for example, why is having some suboptimal behavior good? And there are actually diagrams kind of showing why this is. But essentially, it helps the agent to explore. And so imagine we have some sort of environment where there are multiple high rewards. Just if the agent finds one high reward, we don't necessarily want the policy to be learned to be deterministic. So there are some models that will actually learn the policy to keep going to that one state of high reward, but there could be many others. So that's why we want some kind of like exploration or suboptimal behavior to be able to find even better states. And we will also look at this more later, which is for why this kind of stochastic behavior might be preferred.
Roshni, I
Okay.
try to understand better for this 0102. So it is something that observable, right? And it's also related to the reward, and it's related to the current reward, right? But
yeah, in the sense that all of the states and actions are actually connected to that variable.
yeah, but if we already have this reward, so it's like we already know that the reward function are t, and we can measure that. I just wonder, why do we still need this kind of observable additional information? Because somehow everything has already been captured in that reward function. But do we have some assumption, for example, that the reward is not directly readable, and what we can really observe is something like some feedback that says it's like good action or not?
I think we know the reward, but we kind of just explicitly added in this. So it's useful for later on when we will look at like different objective functions, and then once we have like we start with an arbitrary policy, like in policy iteration, we will see how these optimality variables will actually help us in kind of refining our policy to eventually learn the optimal policy. So we kind of just explicitly have it here, but it's useful for later on when having this.
Great.
I
So you're
suppose
going to
we can.
show some examples later.
Yes,
More
yes.
concrete
Yeah.
setup. Okay, great.
Correct. Yes. Okay, so we just talked about this part. Okay, so what can we do with this kind of diagram? So first, if we are given a reward, we are able to determine what is a likely optimal trajectory. All of these things actually we will be talking about in future slides, but it's kind of represented like this. So remember these optimality variables, because of this here, the way we define it, it actually has this relationship to the reward. So we can denote it like this. And then also, given a collection of optimal trajectories, can we infer the reward and the priors? And then given a reward, can we infer the optimal policy? Now, which is expressed like this. Okay, so we have just defined the optimality to be as follows. And so when we say that, what is the probability of this tau given, or the trajectories given that we have been acting optimally for all the time steps, that's basically the probability of that initial state multiplied by this is the probability that we take this action from that state. This is the transition operator, and this is the probability that we have been acting optimally. So this, the same thing here, we can actually parametrize this. So in other words, we parametrize R to this R of phi and P to P of this theta in this way. And we can write this expression, this one, in this way. And how do we interpret this? So this means that this part is the probability assigned by the environment, and it's how plausible this current trajectory is under the current dynamics. So these are actually the transition dynamics of the environment, and this is that state that we start at. And because we are having this reward here, reward function term, we can interpret this as we are kind of upweighting the trajectory proportional to the reward. So in other words, trajectories that have higher rewards will have higher weights compared to the trajectories which have a lower reward. And when we do this parametrization, we can think of this in like this general form here, where we have a feature weight multiplied by the feature function. And so we have this like FR, which is dependent on the state and action at time step t, which is like this function here, and then plus this other feature weight times feature function, which is like this other term here. And this is similar to this conditional random field in this way. Okay, so remember that when we were talking about the v function and then the q function, we were looking at these computational trees. Now we're going to actually be coming back to that idea by looking at these backward messages, and which is useful for actually computing the gradients when later we want to compute the objective function. So we call these backward messages the beta, and beta of STAT we define in this way, where it's the probability distribution of these optimality variables or the rewards given the state and action. And then we will be computing this. So probability of the action given the state and the reward. And okay, this part is actually not discussed at this point. So looking more in detail into this backward function, the first thing we do is we rewrite it in this form where we introduce this st+1, but we'll see why this is useful coming up. It'll help us kind of simplify our expression to a way that we can actually understand it. So we rewrite it this way, and this we can further rewrite in this way. This is just from this step to this step, it is kind of just following the rules of probability. And the way we interpret this is as the probability of being optimal from the next time step to the horizon. And this is the transition dynamics, and that we have currently acted optimally. And then going from here to here, we, similar to this way where we introduce this st+1, we also introduce this at+1, and then we integrate it out. So it's kind of not really changing what the equation is doing. And one thing we note is this term here is actually beta t+1 of st+1 at+1. And this probability function here is the beta t+1 st+1. Now this is for that very last time step. What about for the previous time step? So we can more generally write this as follows, that for time step t equal to everything previously, so t-1 to 1, we can write the backward messages in a similar way. So it's basically following this. Okay, so this I have just copied here. And now let us just call, this is where the value functions and then the Q functions kind of come into picture now. let us make the relationship between those and the backward messages as follows. So let the value function of the state be the log of the beta t of st, and then the q function of the state be the log of beta t of the state and the action. Then basically by using these three equations, we can easily get this form here. And this is actually applying a softmax. Then we can also derive these two equations here. So it's pretty much, I don't want to go into the details of how you get this, but it's basically just pretty simple algebraic manipulation and rearrangement of terms. But if you use these two equations as well as this relationship, you will easily be able to get these two here, these two equations here. So this is for the deterministic dynamics and stochastic dynamics. The main difference is that in the stochastic dynamic case, we actually have this expectation under this probability distribution here. But there's one thing that we observe from this, in the sense that this is actually too optimistic of transitions, and that is not actually good. And the reason is because if we follow this kind of formula here, then that will actually enable for the model to learn more risky behavior. In other words, to take actions that may have very high reward, but then the overall probability of getting to that reward is actually very low. That in the more likely case, it'll actually accumulate much lower rewards. So in that way, we call this too optimistic, and we will actually later fix this model to make sure it's not as optimistic. But it does actually have to do with these transition dynamics. So this part I will talk about later. Then we can also, once we have these backward messages, beta t of stat and then beta t of st, we can write this policy of this action that we take given the state as follows. And this is basically this part where we have the exponential of the q function minus this value function. And we call this term here, the q minus the v part, as this at, which is the advantage function. And the way we can interpret that is it'll tell us how advantage it is to, let me fix this, to take an action such as in this qt stat, and how that compares to taking an action based on following the average policy, which is this term here, the value function here. And so this derivation is pretty simple. It's basically we just use these two equations here, and we can get this. Okay, so and here's the natural interpretation that we have better actions that are more probable, and it also has random tie breaking. So in this case, we have, the reason why we do that is random tie breaking is because we have this advantage function that instead of being more deterministic towards the optimal q, such as like argmax over the actions of the q as a function, we're actually doing something a little bit different. It's actually the exponential of the q minus v. And this approaches the greedy policy as the temperature decreases. So what is temperature? in the lecture, they mention introducing this alpha variable that that when we do 1 over alpha, say we kind of scale this whole expression, that is actually denoting the temperature. And when we have a greater alpha, then that means this. So in this case, when this term becomes very, very small, then it's that the model has more randomness. But then when we have a much smaller alpha, so this becomes much larger, then it becomes closer to the optimal Q function, which is like doing the argmax of the actions. So that's kind of the idea here. And just to summarize all of this, so again, in this hidden Markov model, we had introduced these observable variables, which we call as optimality variables, that are connecting to the corresponding state and the actions. And then the state and action variables are actually the latent variables here. So we call these optimality variables as the auxiliary variables. And we kind of discuss this, but it becomes very, this is, we can think about this like a hidden Markov model now. Okay, now we're going to, given that we talked about these of forward and backwards message passings in the hidden Markov model, now we're going to look at this from a variational inference perspective. And actually what we will find is that in both cases, either using the variational inference or using this forward backwards message passing in hidden Markov models, we will come to getting the same policy, which is kind of interesting. But we will now look at it from this case. So this we just saw, we define the policy in this way. And this is what we call as inference-based policy. And we just discussed this, where we can rewrite it in this way with the exponential of the Q function minus the V function, which we call this part as the advantage function. And we also know that when we have an optimal policy, that's like saying the policy that is getting the largest expected return or cumulative reward, which is from this value function. Now the idea is there a way that we can find an objective function now by optimization, which we can be able to recover this? So in other words, is there some kind of a bridge between this optimal policy and then this one, inference-based policy? And we will actually look at that now. And the idea is to kind of compute the KO divergence between a policy and the optimal policy, and then find a way to kind of minimize that. So we will eventually reach the optimal policy. So again, this part is the function for the policy. So let's call this the probability distribution over this optimal trajectory tau. And then we have this p hat of tau, which is just an arbitrary policy. And that, let's just define that as being proportional to, this is supposed to be an indicator variable here, not one. And this is that p tau. So it's again using this p tau is not equal to 0. So only certain, in other words, we only consider certain trajectories, and then we kind of weight those by the probability of taking certain actions under that particular policy. And then what we do is we compute this divergence between these two different policies, the optimal policy and then our policy here, which is this here. And we got these two lines here, but we see that some terms actually cancel out. So like this part here will cancel out, and then also this one. So essentially what we are left with is this reward minus this log of this policy of this action given the state. So that's what we write over here. And after that, we see that this term here, which has to do with the reward, we kind of split the expectation, and this log pi function of the policy, we just rewrite this using this h function here. That's doing the same thing here. And when we have this form, this is actually in a recognizable form. And what they say is this part is kind of the standard RL form where we have this expected return, which I talked about in the very beginning. So if we look at one of the previous slides, again, it's like in this form here, where this is like the reward function. And then we have the entropy of the policy, which in other words is telling us how much of randomness is there in this model. In other words, how much will it additionally explore. Now, this is something we looked at earlier. We saw the deterministic dynamics for how we define it for the Q function, and then we saw stochastic dynamics. And we talked about how there was this problem in the stochastic dynamic case where we have this very optimistic behavior that the policies tends to take risky behavior where it will try to optimize the reward, but then in the average case it will actually have lesser reward. So we wanted to find a way to fix that. So there's one possibility if an agent has or gets this high reward at the end. So first is one, it could have learned a very good policy, or the second is it could have just gotten arbitrarily lucky, that it happened to explore some states and that happened to be very good. So now we say this is define this as the expression for the optimal policy. And first we want to be able to do the following, that given we obtained a high reward, what are the good set of actions that we have to take? But at the same time, we see that the model tries to do this part, which is actually what we don't want. It tries to find this optimal transition probability, which in other words is if we obtained a high reward, what is my transition probability? And this part is kind of dangerous because the model could possibly produce these policies that the agent cannot possibly do. In other words, this transition dynamics is something that's inherent to the environment, but this is not something that is really controllable by the agent, right? So the model shouldn't be trying to learn something like that. So we want to do the first thing, find a good set of optimal actions, but we don't want to do the second thing. So what we actually do is a pretty simple fix for this. So remember we had two kind of policies. We first had this optimal policy, and then we had this, which is p of tau, and then we had this p hat of tau previously when we talk about this KL divergence here. So let's use a similar idea where we have these two different policies that we want to minimize the KL divergence for. But let one of them, let's call that Q of tau, which is the, let's define that as the induced distribution from a policy over all the trajectories. And we wanted to actually approximate this p tau, which is the optimal policy, given that we have been acting optimally. And when we want to try to fix this problem, what we do is, now instead of making these, giving flexibility to learn these transition probabilities, we actually explicitly force this. So in other words, when we're trying to find this Q that approximates this optimal policy, we actually fix these dynamics to follow what is in the environment. So we actually have, instead of being Q of this ST plus 1, the next state given the current state in action, we actually fix this to be P. To increase this. Okay, so yeah, apologies for being a little bit blurry, but we can rewrite this Q of the tau to be just like this, as follows. The only thing that is different is that these transitions, we explicitly fix them to be this P of this transition. And then this is the only new thing now. And now let's graphically look at this for a moment. When we have this optimal policy here, and then this is the Q, we can visualize it like this, as a hidden Markov model where we have these optimality variables, which are what's observed or auxiliary, and then we have the state and the actions, which are the latent variables. And when we look at this Q, which is just dependent on the state and the actions, we can visualize this as just a regular MDP. Now let's try to define something interesting, because we're going to try to put this in the perspective of variational inference now. So this is kind of just giving some motivation for how you can think about that. So first is, let us just define X. X, think of it like a vector, or having a sequence of variables. And this is all of the optimality variables from all the time steps. And then the Z, to be all of the set of these sequences of the states and the actions of all the time steps. Now, if we want to compute this P of Z given X, that's like computing the posterior distribution. And if we want to compute Q of Z, that's computing the inference distribution. And this is visually how you can interpret this. So remember, these are like our observed variables, and these are the latent variables. So we can model P of Z given X in this way. And the inference is the other direction, where it's Q of Z. Okay, so let's go back to what we just discussed with the two kind of policies. This is the optimal one, and this is the one that we just defined. And this part is, we take actions according to the state, but this is given by the current policy, and we are fixing the transition dynamics to follow that of this. Then we want to maximize the likelihood of these observable variables, which are these optimality variables. So we can express it like this, as the log of this double integral of the P of the optimality variables, all of the states and the actions integrated over this, the S, all of the states and the actions. And then what we can do, this is actually no difference, but we can rewrite it like this, where we introduce the additional term. And then we convert this integral to an expectation. So that's kind of what we do here. We get these two terms, and then this is an expectation under this distribution of following this arbitrary policy of the trajectories. And by using Jensen's inequality, we can actually simplify this part to be this. Okay, so this is okay. This part here is just rewritten in this way, and many of these terms again cancel out here. So it's this term, these two terms, and we have this, which is very similar to what we had just seen earlier, where we in this form again we define this log of q to be of this h function. So this is again like the standard RL component, and this is the entropy of the actions. Okay, so one thing we saw now, given that we have this, we now are trying to use this in the variational inference setting. So when we want to kind of optimize this, we optimize the evidence lower bound, which is this part here, which we just saw from by simplifying it to this expression here. Now for the base case, which is that last time step of t, we will derive an expression, and then we will look at all of the previous time steps between 1 to t minus 1. So in this case, we can see this here, and remember the h function is just as this log q part. So we write it like this, and they don't go through all of the steps on how it's being minimized here, but essentially the final result is that it is proportional to the exponential of this reward function. And this is just normalizing this q of a given s, which is that policy at the last time step. And this part is basically this. It's the exponential of the capital Q function minus the value function. And this part we can see because it's there was, remember that relationship between the value function, the Q function, in that if we kind of integrate out all of the actions of the Q function, we kind of get the value function back. So that's what we are doing here. And using that, using that, we get this part. Okay, so now the question is, how can we write this for all of the previous time step from 1 to t minus 1? So we saw this for the case of the last time step t. Now, the only difference between this part and this part here is that we have this additional v of st plus 1 because we are dealing with all of the previous time steps. This is not the last time step. So we have this additional term here. And this part is actually the q of stat. So we can write that. And again, this h function is a log q. And when we solve this, we find that this q for all the time steps from 1 to t minus 1 is proportional to the exponential of the q function of the state and action. And we know this again from here, this part. And we already saw this part, which is from up here. And using this, because it's proportional, we can actually say that now that the Q function is this reward plus it is the expectation of this value function at the next time step. So it's that value function is the expected cumulative reward. So in this case, that is for the next time step. And what we note here is this part is not as optimistic. So when I go back to this one here, we see that first of all, there's this exponential, which is kind of distorting how good the rewards are. So rewards that are already very high, when you take the exponential of that, it becomes even bigger. So there's that, and we applied this term here, this logarithm here. So this part is a little bit different from this. And the other thing is in this model, we gave it flexibility to kind of control this part, this transition dynamics, but we wanted to make sure that we actually fix it so we don't have the agents to learn policies that are not in its control. So because we explicitly fix it, this part is actually taken care of. So this is the final equation we have here, and it's not that optimistic. Okay, so this part we just looked at, so I don't want to talk about this right now. Okay, so now we go to part 2, which is actually building up on what we learned from part 1 about the Q function, the value function, the policy, and so on. Okay, so this is now part 2. And we're going to look at more interesting things now about how to kind of refine our policy if we don't already have one, both if we need to assume that there's an existing policy, which is in policy iteration, and then how do we do this without even having the existence of a policy? So this is in the case of value iteration or Q learning. Okay. So again, this is how we are defining the various different terms here. This is the initial state, S. This is the transition dynamics. This is the policy, the reward function, and then lastly, the idea of optimality, where if we have trajectories with higher rewards, we kind of upweight those. And we had seen the value function and the Q function from previously by following this policy, pi. And this is what the corresponding computation tree looks like, where instead of enumerating over all of the actions like previously, when we take the argmax of that, then we actually get the optimal V and the optimal Q. And if we want to be able to recover the policy from the optimal Q, this direct delta is not really in scope, but if we want to do that, then this is like an inverse RL problem where we kind of take the argmax over all of the actions and then apply this delta function to get that optimal policy. But this part has to be the optimal Q. Okay, and then when we introduce the notion of the optimality variable, the O's here, we also said how can we, given the reward, get the trajectories. So this part can be rewritten in this way, where we have the the initial state, then these are following the transition dynamics from the environment. And this part is we are kind of weighting that by the reward. Then we also define the idea of these backward messages here. And we express the relationship between the V and the backward messages as well as Q and the backward messages. And finally, we actually derived this here, where we have a connection between the VST and then the Q of that state in action. And we said this is using a softmax. And when we have this this is following that optimal policy, because here we have these optimality variables. We said that that is equal to this part, just the exponential of the difference between the Q function and the V function. And this is what we call the advantage. So this is, in other words, if we now have, if we now introduce a new temperature variable, which is the 1 over alpha, this is kind of controlling how entropically this is behaving by this VT term, versus if we have alpha to be much lower, then it's behaving like a more greedy policy, more closer to the optimal Q function, which is the argmax of the actions of the Q function. So that's the idea behind this advantage function. Then we saw something interesting, which is if we start with an arbitrary policy of P hat, and then we have this optimal policy of P, we can compute the Kullback-Leibler divergence and minimize that to try to get this optimal policy. And we call this P hat to be policy induced. And this part, we can rewrite this as tau given the optimality variables as the optimality policy. And we saw that it is in the form of this standard RL objective, and then we have this entropy of the actions. Okay, and when we look at this here, with the state, the action, and then the optimality variables, we can see that it can be used for different things. So this, we can have it in these 3 different terms. And this part, we will see that it is actually used in behavioral cloning, or in other words, imitation learning, where given that we have an expert that we are observing different policies from, or different trajectories from, then we essentially just want to kind of imitate that behavior. Then we have this case where this is used for imitation, inverse RL and planning. So we want to be able to select the action that will kind of lead us to the optimal trajectory. And this is the standard RL case. And if we look at each of these different ones, these are the given. So we have the, in this case, imitation learning, we have the taus, or the trajectories. And this is the objective here. In this case, in the inverse RL case, we have both the trajectories and the optimality variables. And this is the objective. In the planning case, we also have tau and the objective variables. So it's this one here. And in the RL case, we just saw this, but we just have these optimality variables, and then we try to do this log P of this. Okay, so now we're going to look at some policy gradient methods. So more generally in RL, we have this reward function, and we kind of want to find these parameters, theta star, that will be able to maximize the cumulative reward. And this is the general learning framework. First is that we generate some samples by running a policy. So this is obviously assuming that we have a policy, but later on we'll actually find a way that we can find a direct relationship between Q and V without having this policy. But for now, we have a policy. We generate samples, then we fit a model and estimate the return from those trajectories, and from that we get a policy and improve it, and from that new policy we again repeat the process. So we keep kind of refining this policy until it reaches the optimal policy. So this is a very high level overview. So now we're going to talk about this in more detail. Okay, so this is just kind of giving an example that RL is useful and can be kind of transferred to the real world, because this is like an agent that is following policy iteration to learn how to walk correctly. Okay, so there are many different kinds of these RL algorithms. The first one is using policy gradients, where we directly optimize this stochastic objective function here. The second case is value-based methods, where we are estimating the V function or the Q function of this optimal policy, but we are not giving an explicit policy. But here we can actually have the policy that is derived from the value function, or in other words, remember previously that we compute this Dirac delta expression of argmax A of Q, which is this part here. So we can also do this from if we have the Q function. This is the next one, which is actor and critic, which is to estimate the value and the Q function under the current policy and use that to improve the policy. So we can split this into, say, 3 different steps. The first one is to separate the set of parameters for this value in the Q function. And the next part is then have another set of parameters for the policy function, and then kind of iterate between optimizing the first set of parameters for V and Q and then the policy parameters. And then we also have these model-based methods. This part is actually not really in scope. What we're really going to focus on in this lecture is the first two, but this is just the policy gradients and the value-based methods. But this is just to tell you that there are other methods as well. For example, in this one, we estimate the transition dynamics for the model and use it for planning, such as selecting optimal actions or using it to further improve the policy. Okay, so again, this is the main focus for today's lecture. So this is the same function that we saw above over here. And this part, we can actually call this J of theta. And note that this part is an expectation of trajectories generated under the policy. That's this P of theta here. So let's follow the first step here, which is now generating these trajectories. And how we do that is pretty simple. We first start with S1. This is the initial state, And then for all of the time steps, we kind of follow the policy. We run that, and then we get this action. And then we get to the next state, and we accumulate this reward. And so we can do that to generate a bunch of trajectories. And say we generate n trajectories, then we can actually get this Monte Carlo estimate of this objective function, because here it's an expectation, but here we can kind of sample. So there are again n trajectories here. Now, if we want to compute the gradient of this thing to optimize the objective function, one thing we note is we cannot actually do that here, because this doesn't really depend on theta, even though we can see that, of course, this here, when we generate the trajectories, the policy is dependent on theta. So we kind of rewrite this in a nice way. So we have the gradient here, expectation of this r of tau, and we can rewrite this as an integral of this reward r tau of this gradient of the policy of tau. And this part we call as the reinforced estimator. And then what we can do, so we are at this part here, we can apply this log trick. So when we have this term here, this part, we can rewrite it as this. So that's how we get this expression here. Okay, so this is just some more information if you want to know how this is being done. Okay, so now we have this a gradient with respect to theta of this j theta objective. And it's basically this over here. We note that this is just, again, a definition of this part, but it's the P of the initial state, and then we have the transition, and then we follow the probability of taking these actions of the policy. So some of these terms cancel out, and the reason is because they have no dependence on the theta, so the gradient is of course going to be 0 here. So basically this term, this is for simplifying this part here, but then we also have this reward. So we can now convert this part into this from here and then from here. And so we see something interesting now. This is what we just this is the current gradient of the objective function we just derived, but this is from the MLE case. So this is from the probabilistic graphical model. This is from MLE, and here the difference is we have this additional term of these rewards that we're kind of waiting. So the interpretation is we sample many trajectories and update and upweight those with higher rewards. Versus in this case, we don't do that because we are already learning trajectories from the expert. So we're kind of just imitating that. So we don't have to upweight anything. And this is just an example of this part. This is just illustrating that. So we have like trajectories with higher rewards. So we're kind of upweighting that. And then we're kind of downweighting those with lower rewards here. Okay, so this is this gradient of theta of j theta. And again, this expectation now we can use sampling to estimate it this way. So this is the approximation. This is how we convert this from this. And now we're going to talk about the reinforced algorithm. Okay, I'm not sure why it cut off here, but it's basically this part where we are first sampling these n trajectories under the policy. And then we have this objective function where we are kind of upweighting these trajectories by the rewards. And then once we have this objective function, then you can kind of use your favorite optimization method to kind of find these different parameters. So and this is just an example of gradient descent, but you can actually use any of them. And here's the idea. So first, we are representing this policy with a parametric function, and then so that's how we're introducing these thetas, and then we are learning it by optimizing this reinforce objective, which is the step 2. And now I mentioned this earlier, but there's actually an interesting relationship between this probabilistic, this graphical model objective versus this MLE objective with the rewards here. So remember, we did a comparison of these two things, and we have this additional reward term. So we're kind of upweighting trajectories here, but in this case, we're kind of just imitating this expert. So that's the idea here. One thing we observe is that the gradients with this reinforce algorithm often have extremely high variance. So again, this is what that is. And that could be bad because that means there's a lot of noise which can slow down the learning of the algorithm. Another thing that could likely be the case is that for these rewards, it could be very sparse. So in other words, most of the time it could actually just be of value 0, and only a few times could it be non-zero. So that actually means that there's much less signal for this to learn, because if this is 0, the whole thing will become 0. So there's a lot less signal to be able to learn these parameters. And then this part here is actually not really in scope, but this we can actually make use of action causality and value estimators to be able to help solve this issue. And action causality is when we upweight the actions proportional to the cumulative returns that the action actually affects. Okay, so one thing we did see is that for policy iteration, it's very dependent upon actually having this policy. So is there a way that we can actually get rid of this policy altogether? Because if you remember previously, we generated samples by following this particular policy. Okay, so one thing we need to see is what kind of relationship can we kind of establish between the policy, the Q function, and the V function. And this will actually help us to get rid of this dependence on the policy. So just to recall, when we find this optimal policy, we do that by computing this delta function over the argmax of this Q function. But then what happens if we don't have this optimal Q function? Maybe there's a way to still be able to do this. And the answer is yes, we can do that. We can, for now, just assume an arbitrary policy, which is Q of pi here, and then kind of converge to the optimal. So just like we were improving the policy, we can kind of do something like that here, where we're like iteratively improving this Q. Okay, so that's kind of the idea here. Can we learn a Q function through interaction with the environment without a policy? And remember that if for all of the states we have that accumulated return by following that particular policy is better than the cumulative cumulative return from the other policy, then one policy is better than the other. So when we are doing this argmax operation here, and then we are applying this direct delta, we can actually say that this pi prime would be better than pi because we're doing this argmax explicitly. And then we can actually have this better policy. So, and this is actually dealing with policy iteration. This is not yet getting rid of the policy. We will actually see that in value iteration, but this is for now using the policy and iterating upon that. And here, when we find the returns, we're actually fitting this Q function here. And using this computation tree, we can see something similar here, where we have the states, we have in this nodes, and then these black nodes are the state action pairs, and this is the next state as prime, and we can keep expanding upon this tree until we kind of get to these leaf nodes, and then we can roll back up to be able to compute the Q function, right? Because from the value function, we can compute the Q function. Remember that if we kind of integrate over all of the actions of the Q function, then we can get the value function. So there's actually a relationship there. And we are taking actions according to this policy. Okay, so from here, I'm just rewriting this here. Then remember, we need this v function here. Then we apply policy iteration, and here we need to start, of course, with a policy. We evaluate this Q pi under this policy pi. Then we use this argmax, right? And then we compute this new policy. And after that, with that new policy, we again find the value function. And then we keep repeating this process. So it's kind of like a cyclical process here, because this is then being used as the v pi here, and then we continue onwards. This is visually what we observe with policy iteration. So remember, we were starting with this arbitrary policy pi. So this is v pi, and then we keep updating this v pi. So we start with this, we compute the Q, then we evaluate that, we update our policy, and then we compute the new v, and then we compute the Q, and we keep doing this. And eventually we see that this will actually converge to the optimal value function with under this optimal policy. So that's the idea here. Okay. Now this still goes back to the original question where we had this dependency on this policy. How can we get rid of this dependency? So that's when we talk about value iteration. And remember this equation from previously where we can get this policy by applying this delta function of the argmax of this Q function. Now, the idea in value iteration is before, let's look at policy iteration first. We had this dependency between V to Q, then to the policy, and then back again from V to Q to the policy. Now, is there a way to remove that policy dependence and just go from V to Q? And that's what we look at here. So we know that we have this. We've seen this from before. But we also do know that when we take the max of the actions of Q, the Q function, we actually get the V function. And if they were both optimal, so this is the optimal Q, then we get the optimal V. So this is actually in the optimal case, we have this. But the idea is that we keep doing this, and eventually we will actually follow this behavior. But there's one problem here, and the problem is with this Q. So let me take a step back first. So in this case, we imagine this in like a tabular fashion, that we store all of these variables. We have the states and then the actions. And then we use that to compute all of this, the V and the Q. But now the question is, what if this Q function is very, very high dimensional? We can't really afford to do that. We don't have enough memory capacity to be able to do that. So what we can instead do is now find a way to approximate it using this parametric function. So let's try parametrizing this. So we previously parametrized the different functions in the past. So let's do that here too. And this is with Q learning. So here what we do is we rewrite this part here to this, and we observe that, like we said before, in the optimal case, we have that this term here is the max over the actions of this Q phi function. And then we can apply regression to basically compute this phi, and we have this Q parametrized by this phi. So this would be the algorithm then. We would have this data set where we have the states, the actions, the next state, and then we would have the reward from that under some policy. And then we would compute this yi in this way. And this is the discounted variable of this expected cumulative reward. And then we would apply this. This would be our objective function, and we would solve this similar to like a regression problem. And we can actually keep on going from here, from step 2 to step 3, to eventually try to make this loss as close to 0 as possible. And when it is actually 0, in this case, then we can actually see it follows optimal behavior, where it follows this. And this is actually what we want. This is what the optimal Q should look like. So at that point, then we know that when we have this optimal Q, then we have this optimal V, and then if we have the optimal V, then we know we have the optimal policy. Now there's one more interesting thing you may think, which is we saw before that when we computed the KL divergence by of this P of tau, P hat of tau, and this P of tau. So one is arbitrary policy and one is the optimal policy, and we want to try to minimize this divergence. We had this objective function, and now you could ask, what if instead of using these other objective functions, what if we kind of just use this one? Can we still solve it? Okay, can we still find like the optimal? Can we still use this objective function for finding optimal policy for policy learning and Q learning? And the answer is actually yes. And we will look at that case right now. So remember we had this, where this is the parametrized version, where these are the parameters theta star, and we have this objective function. And we can write it up this form. Okay. And this form, remember, is this part here. So we're using this directly as the objective function. So that's how we get this. And then we are directly computing the gradient of this, gradient of theta. And remember, this h function is actually this log of the policy. Okay, so one more thing is that we observe something, which is here when we have this p of which is that optimal policy of the action given the state and the reward. Remember, we had said that this is the exponential of this q function minus the v function, which is this line here, and we know that this v value function is basically the integral of the q function. So we can use this, and this from here to here we are using sampling instead of taking this expectation. This is the approximation we're doing. N is the number of trajectories, and there are actually quite a bunch of other steps here that are not included. This is just to give you an overall idea of what this is doing. And this part here is approximately the q of the next time step. And when we finally expand this and simplify, we get this here, which is where we have the softmax expression, but then this is following this part. So this is actually, this whole term is v of st plus 1. So because we are using the softmax, this is actually called soft Q learning instead of Q learning. And there are some interesting things that we observe from soft Q learning as compared to Q learning. First of all, we just denote that here, but let's talk about Q learning first. This is this is just following the gradient descent, where we have this theta as the parameters, we have this alpha, and this is basically that objective function. So this step 3 here, when we substitute y to be this, we actually get this expression. So that's what it is. This is the gradient of that objective function. And in soft Q learning, it's actually the same thing. The only difference is here now we're applying a softmax instead of just a max. And comparing the two things, we see something in practice, which is that when we are using the softmax, we actually enable the agent to be able to explore more states while also reaching the regions of high reward. So this is from a paper in 2017, and it's a bit complex here, but this diagram is basically a multimodal distribution of rewards in a two-dimensional environment. And this agent here is in these like the node circles here. So it's green and pink. This is showing the pink one. But you can see that it actually explores the whole environment. And it does indeed reach all of these high reward states. It doesn't just go to one, but it reaches all of them. And that's the interesting thing we see with soft Q learning, that it has a good balance between this exploration of the space, but it also is able to kind of maximize the objective, and it's able to get these high reward regions. So we see some benefits with this soft optimality, which is that it improves exploration like here, but it also prevents entropy collapse. And what entropy collapse is when I hinted towards this before, but if we have an environment, say in this one, that have many states of high reward. So in this case, there's 4. It's basically more than 1. If an agent is following entropy collapse, that means once it finds one area of very high reward, the model learns the policy to become more deterministic, to always just keep reaching that particular region instead of still exploring other places of high reward. And that could be bad because this could still just be like a local optimal point of that particular reward state, right? But there could be a lot more with also high rewards. So this soft optimality actually prevents this entropy collapse phenomenon. The other thing is that empirically, it's seen that the policies are easier to fine tune for more specific tasks, and there is a better robustness because it's able to cover more states, it's able to explore more. And it can also reduce to hard optimality. And this is what I had shown before, where we have that 1 over alpha term. I'm trying to find that. Okay, here. There's this 1 over alpha term, and remember, when we adjust the temperature, so we have this greater alpha, then we are following a more random model. It has more entropy. But then when we have a smaller alpha, then this thing becomes very large. So we actually are closer to the optimal Q, which is the argmax of the optimal Q. So we can actually introduce that 1 over alpha term to adjust this optimality. And the last thing is that it could be a good model for human behavior, because human behavior is not always very deterministic, right? Because there's still some randomness. And because of this good property of exploration while also being able to prevent this entropy collapse, this model of soft Q learning works well in practice. And lastly, just some summaries. This probabilistic graphical model, it provides a unifying perspective on sequential decision-making problems. And we saw that there's a special relationship between probabilistic graphical models and maximum likelihood estimation, where we see that the trajectories actually are weighted by the rewards. But then in this case, we learn a policy that in MLE, we learn a policy to just estimate what the expert is doing by following that. And another interesting thing we see is that these recursive optimality relationships in RL, they're recursive because, of course, we see that the value function, the Q function, can be represented recursively. They also have these soft forms where they use this softmax function, and that is that's interesting. And lastly, these algorithms do work well in practice. So that's the end of the lecture. Thank you.
Thank you, Roshni. So I think it contains lots of content. So I'm quite interested in this like soft Q learning. Can you explain what does this soft max mean here exactly?
Okay, so I think the difference between this and the regular Q learning, actually, maybe this is a better indication. So this is actually directly comparing it, but here the softmax is actually when we do this log of this part. but instead of just applying this max. So I think
So
that is the difference.
I try to like understand it without math. So for the this hard version, it seems to me it's like, okay, we just select the best action that can maximize this Q function, right? And then we're going to use that to define the value function for the S prime state. For the softmax, do you mean that we're going to kind of measure, we're going to assign a probability, a soft probability to different action? And then this VS prime is going to be a kind of weighted combination of that Q function?
Yes, it is actually like a soft probability, and that's actually why they say that it enables the agent to explore more, because it's there's still a very, even though probability may be low, there's still some chance that it is able to explore some states that at the time may look like it's like more inferior, but then could lead to higher rewards, such as, for example, say this agent is only learning to go to this region here. There's still like a small probability it could take a step in another direction, say going up north, but that actually leads to, say, a higher reward. So we still have some chance it does that.
I see. Yeah, I think I got it. Thank you.
Thank you. These slides, I've actually also shared the link to them to these slides in the email, so I think everybody should have access to it.
Okay, great.
Hi, sorry, I have a question. First, thank you for the presentation. I just want to have more understanding on the design or the learning of the reward function, because it seems to me that the whole framework makes a lot of sense if you have a clear idea of the reward, such as when you're playing a game like chess or Go. But in a real world scenario where your states may not be discrete and your reward is very hard to define, such as in a self-driving car scenario. In that case, I wonder, how do you define the reward for the environment, or is there like a learning process for that?
That's actually a great question. I actually was wondering the same thing too. So this is more of just a framework for learning, given that we have that hidden Markov model, right? So in other words, we have some particular particular states. We have the actions we can take that's only allowed by what's in the environment. We have transition dynamics, and then we naturally have rewards. So we're actually, the setting we are dealing with is we are actually given all of these components, the S, the A, and the rewards. So how to define that is actually quite interesting. But I one idea that I had was that maybe there's a way that we can learn these rewards by following a mechanism similar to how we learn the policy. Of course, we are assuming that we are already given this hidden Markov model, right? But your question is like, what if we don't really know the rewards? How do we find something good? So I have a feeling that maybe we can do something similar to this, where we kind of have many samples, and then we are able to learn what is a good or representative reward.
Yeah, so right, like I'm not very familiar with the paradigm, but it seems to me that it's, if you have like two unknowns like policies and reward, is it possible to do some optimization that's in the scheme that's similar to like EM algorithm, or a coordinate kind of update? Is there some like existing work on that, or no? Or and is there like a latent representation kind of framework behind the Markov decision process?
Yeah. So that's actually, that's a good question. This is definitely not going to be proper to solve that, because remember, in this way that we denote it, we have the optimality variables to be observed, which are encoding the expectation, the exponential of the reward function. So we actually observe the reward, but your question is more of what if we don't? So it's not covered in this lecture, but I think we can perhaps learn that through like a variational inference method.
Okay, thank you.
Okay, great. Thank you. So due to the time, probably we just stop here.
Okay, thank you, everyone. And if there are more
Thank you.
questions, please feel free to email me.
Great.
Thank you.